Okay, so the standard base solution by titration, essentially what we're doing is we're trying to work out its concentration to as many sig figs as we can. And we can do this if the acid that we're using is something that's a solid acid, so we can weigh it out using a balance to a high number of sig figs, so we know very accurately what mass of acid we've used. Therefore, we know very accurately how many moles of acid we've used. So we will also know how many moles of base it takes to neutralize that. And if we're using some very accurate glassware, such as a burette, again, we'll know the volume of base dispensed to a high number of sig figs. So that gives us like the maximum number of sig figs that we can calculate our concentration to. So our basic plan is that we're going to take the mass of our acid, which is our solid, okay? I should put solid acid, I guess. And then we're going to use the molar mass to get to our moles of solid acid. And then we'll use our mole ratio from our balanced chemical equation to get to our moles of our base. And then if we have our moles of our base and we know what volume we've used, we should be able to get to our concentration of our base. If we just divide through by that volume, that'll be in moles per milliliter. So we want to get that into units of moles per liter, right? So moles per milliliter in this case, and then we'll want to get to the concentration in moles per liter. So that's our basic plan, okay? So in this case, our solid acid is our oxalic acid, so H2C2O4. And our base is going to be sodium hydroxide. So what we really have to have before anything else is a balanced chemical equation, just like for any of these other questions. So I guess I should put some arrows in. I can come back and edit this in a minute when I've got some numbers. I need numbers. Don't attempt anything without the balanced chemical equation, right? That is the rule. Okay, so what have we got? We've got oxalic acid, so acid plus base is going to give us a salt plus water, same as any other neutralization reactions we've been doing. We've been told it's a diprotic acid. If we weren't told, we can guess from the formula, because they very helpfully put those two ionizable protons on the front. So it will break apart into two H pluses, and the oxalate ion, C2O4, which has a 2- charge overall, okay? And sodium hydroxide is going to break apart into the sodium cation and the hydroxide ion. So it's going to take two sodium cations to balance this 2- oxalate ion. So the formula of sodium oxalate should be Na2C2O4 as an FYI. And then water is our other product. Remember, acid plus base gives salt plus water. Okay, so to balance it, obviously I've got two sodiums over here and only one over here, so let's make that sodium happy. Oxalate is balanced. What about hydrogens? 1, 2, 3, 4 hydrogens. So I'm going to need, boom, a 2 here. Okay, so let's work out our molar mass of the oxalic acid before we begin. Note, it doesn't matter how much distilled water the oxalic acid is dissolved in. So, for instance, ALEKS tells us that this 236 milligrams, I've got to convert milligrams to grams, of oxalic acid is dissolved in 250 milliliters. It could be dissolved in 50, it could be dissolved in 500. That will affect the concentration of oxalic acid, but that's not what we need. We need the number of moles of oxalic acid. Remember, reactions occur on a mole-to-mole basis. So anyway, molar mass, so 2 times 12.011 plus 4 times 15.999. So the molar mass of oxalic acid is about 90.032 grams. Okay, but we do have to get from our mass in milligrams to our mass in grams. So there is a little bit extra we got to do here. Mass in milligrams to mass in grams. So our conversion factor there, I'm sorry, I'm going to be like running out of space, is going to be using the SI unit prefix. So 1 milligram is 10 to the power of -3 grams. Okay, so we're going to stick that on the front there, over there. Okay, sorry. Okay, 236 milligrams then. So 1 gram, sorry, 10 to the, where is it gone? Minus 3 grams, that's supposed to be a minus, is 1 milligram. So let's get that equivalency in there as a unit conversion factor pronto. All right, so we converted milligrams to grams. Now we can use molar mass. So the molar mass was 90.032 grams for every 1 mole of oxalic acid. Expand the box. All right, then from the balanced chemical equation, for every 1 mole of oxalic acid, it is going to react with 2 moles of sodium hydroxide. I got distracted by that milligrams to grams and didn't write it in here, did I? So I should probably do that. There's our equivalency we're using. To get from the moles of sodium hydroxide to the concentration, we're going to do that concentration equals moles per litre, but we've only got milliliters, so we'll do moles per litres first, milliliters first, and then convert to moles per litre. So we're literally going to just divide whatever that is by the milliliters, which in this case was 129.6. So moles divided by 129.6 milliliters. And then we're going to use that conversion factor for moles to liters, which will be at 1 milliliter is 10 to the minus 3 liters. So that is the plan, okay? All right, so we've converted milligrams to grams, grams to moles of oxalic acid. So then we're going to use that mole conversion to convert between moles of oxalic acid to moles of sodium hydroxide. So this is the fun bit. We're going to divide through by the volume dispensed, which is 129.6 milliliters. Bear with me on units, okay? So as of right now, we are not done because our units are going to be moles per milliliter. And we know that concentration units, or molarity, if you're a chemist, is moles per liter. So all we got to do at this point is convert moles of sodium hydroxide per milliliter into moles of sodium hydroxide per liter. So that is fairly straightforward. We're just going to do a milliliters to liters conversion there right now. 1 milliliter is 10 to the power of minus 3 liters. And that should take care of everything. So she says. Okay, and I straight away just crossed out the wrong thing because I wasn't paying attention. Okay. All right then, so 236 times 10 to the power of minus 3 divided by 90.032 times 2 divided by 129.6 divided by 10 to the power of minus 3 should give us a tasty concentration, 0.04045, blah, blah, blah. How many sig figs does it ask us for? 3 significant digits, so that's 405 moles per liter. If we're doing standard scientific notation and using the molarity symbol, it would be 4.05 times 10 to the minus 2 units of molarity. All right. Okay. So I think that was just the first one I did. So let's just look at another one just to see what else we kind of get. That's the same thing with different numbers. That's diprotic. That's diprotic. Well, now it looks like all these questions are basically going to be for a diprotic acid with a sodium hydroxide. It might mess around with milligrams versus grams, etc., but they are all very similar calculations. So I'm not going to do any more of those because I think one is enough. Otherwise, you know, you're not going to get any practice. And you need practice. This is the most important thing, is practice.